Hello everyone, this is Abhishek Mohanty and welcome to lecture number 10 of the chapter Electric Charge and Field. In the previous lecture, we had discussed about electric dipole moment and the expression for electric field due to a dipole at its axial point, at the equidal point and at any arbitrary point. Today, in this lecture, we will discuss about another important topic, and the topic name is the torque acting on an electric dipole in a uniform electric field. So let's get started. So students, just look at the diagram here. We have a uniform electric field which is represented by parallel and equispaced electric field lines, and the strength of electric field is E everywhere. Uniform electric field means the strength of electric field has the same magnitude and the same direction at every point throughout. And inside this uniform electric field, we have an electric dipole which consists of two charges, minus Q at the point B and plus Q at the point A. And the separation between the two charges is 2A, or we can say that the dipole length is 2A. We know that the dipole moment is directed from the negative charge to the positive charge. So in this case, the dipole moment will be directed from this negative to the positive charge, means from B towards A. So this arrow mark represents the direction of the dipole moment, and you can see that the dipole moment vector makes an angle theta with the electric field vector. So theta is the angle between P vector and E vector. Is that clear? So now we have to derive an expression for the torque acting on this dipole. So students, we know that whenever we place a charged particle inside an electric field, it experiences an electrostatic force. So the dipole consists of two charges, and the two charges are placed inside this electric field. It means both the charges will experience some electrostatic force. And remember that a positive charge always experiences force along the direction of electric field, and a negative charge always experiences force in the opposite direction of electric field. The two charges have the same magnitude, but they have opposite polarity. And since the electric field is uniform, it means the electric field intensity has the same magnitude at every point. The magnitude of electric field intensity at the point B is same as the magnitude of electric field intensity at point A. It means the two charges, they have the same magnitude and they are placed at the same electric field intensity. Means both the charges will experience the same value of electrostatic force, but the directions of the force will be different, because as I had told you, a positive charge experiences force along the electric field and a negative charge experiences force opposite to electric field. So at the point A, we have a charge plus Q, a positive charge. So this positive charge will experience a force along the electric field direction. And what is the value of that force? F plus Q vector is equal to Q into E vector. Q into E vector. And similarly, the negative charge will experience a force opposite to the electric field direction. So F minus Q vector is equal to minus Q into E vector. You can see that here I have given a negative sign, and the negative sign indicates that the force on the negative charge is opposite to the electric field direction, and here the force on the positive charge is along the electric field direction. So the dipole experiences two equal and opposite forces. So the net force on the dipole, will be how much? The net force is equal to F plus Q plus F minus Q, means force on the positive charge plus force on negative charge, and you have to add them vectorially. So F plus Q is Q into E vector, and F minus Q is minus Q into E vector. So the net force will be 0. And we know that when the net force on a body is 0, it has no linear acceleration. It means this dipole will not be accelerated. This dipole has no linear acceleration inside this electric field. Means it cannot translate. It cannot translate. Or you can say that the net translational force, on the dipole is 0. Is that clear? But look at the two equal and opposite forces. Their lines of actions are different. The force F plus Q is acting along this line and F minus Q is acting along this line. They don't have the same line of action. And in class 11 we had discussed that if a body is acted upon by two equal and opposite forces, and if they don't have the same line of action, then those two forces, they form a couple, and the couple exerts a torque on the body. For example, suppose you will take a rod, and if you apply two equal and opposite forces like this, suppose you will apply a force of 5 Newton towards right and a force of 5 Newton towards left, then you can see that these two forces, they have the same line of action. They have the same line of action. And that's why these two forces cannot rotate this rod. But if I apply the same two forces like this, 5 Newton in this direction and 5 Newton in this direction, then what will happen? These two forces now don't have the same line of action. This force is acting along this line and this force is acting along this line. And when we have two opposite forces which don't have the same line of action, they will form a couple, and that couple will exert a torque on the body. So you can see that on the dipole, two equal and opposite forces are acting, and these two forces, they don't have the same line of action. That's why these two forces will form a couple, and they will exert a torque on the dipole. So what is the formula to find the dipole? To find the torque acting on the dipole? The formula for the torque is magnitude of either force into perpendicular distance between the forces. So this is the formula to calculate the magnitude of the torque. Torque is equal to magnitude of either force into the perpendicular distance between the two forces. So the question is, what is the perpendicular distance between these two forces in this diagram? So F plus Q is acting along this line, F minus Q is acting along this line. The perpendicular distance between these two forces will be this one. Draw a perpendicular from this point A onto this line. This one will be the perpendicular distance between the two forces. Means AC is the perpendicular distance. Is that clear? So torque is given by the symbol tau. So torque equal to magnitude of either force. So we have two forces and both of them have the same magnitude, and while writing the magnitude, don't write the negative sign, always write the positive sign. So magnitude of force will be Q into E. And now we have to find this perpendicular distance, means AC. So look at this triangle ACB. In this triangle, AC by AB will be equal to sine theta. We know that sine theta equal to P by H. So AC by AB will be sine theta. That implies AC equal to AB sine theta. And what is AB? AB is the dipole length, that is 2a. So AC will be how much? 2a sin theta. So in place of this perpendicular distance, I can write 2a sin theta. So torque is equal to Q into 2a into E sin theta. And Q into 2a is the dipole moment P. So torque is equal to PE sin theta. Torque is equal to PE sin theta. So this is the magnitude of the torque acting on an electric dipole if the dipole moment P vector makes an angle theta with the electric field E vector. P into E into sin theta. And this torque is perpendicular to the plane which contains P vector and E vector. So you can see that this plane of the board contains both P vector and E vector. So the torque tau has a direction perpendicular to this plane. And remember that torque is a vector quantity. So in vector form, how to write torque? In vector form, torque can be written as P vector cross E vector. In class 11, we have studied that A cross B is equal to AB sin theta. So P cross E will be PE sin theta. So tau vector is equal to P vector cross E vector. Means the torque is equal to the cross product of dipole moment and electric field. Now the question is how to find the direction of tau vector or how to find the direction of torque by using the right hand screw rule. So what is right hand screw rule? So tau vector is equal to P vector cross E vector. So the first vector is P, the second vector is E. So to find the direction of tau vector, you have to rotate P vector towards E vector. You have to rotate P vector towards E vector. Look at the diagram. P vector is in this direction and E vector is along this direction. P vector is along this direction and E vector is along this direction. So in this case, to find the direction of torque, you have to rotate the first vector, means P vector, towards E vector. And here you have to rotate it clockwise. So when you are rotating a screw clockwise, it will go inward. And if you rotate a screw anti-clockwise, the screw will come out of the wall or out of the board. So remember that if P is rotated clockwise towards E vector, then the torque will be inward. And if P vector is rotated anti-clockwise to E vector, then tau vector will be outward. So for clockwise rotation, tau vector is inward, and for anti-clockwise rotation, tau vector is outward. So you can use the right hand screw rule or right hand thumb rule to determine the direction of the torque acting on the dipole. So this is all about the torque on an electric dipole which is placed inside a uniform electric field. Now we will discuss about some special cases. So the magnitude of torque is PE sin theta. So the first case is when the P vector, means the dipole moment, is parallel to E vector, means theta is equal to 0. In that case, sin theta will be 0, because if theta is 0, then sin 0 is equal to 0. So in that case, torque will be how much? 0, because torque equal to P is sin theta. If theta is 0, then sin theta will be 0, and hence torque will be 0, means no torque act on the dipole. So remember that whenever there is no net force on a body, the body is said to be under translational equilibrium. Similarly, if there is no torque acting on a body, the body is said to be under rotational equilibrium. So when the dipole moment is parallel to electric field, the dipole will be under rotational equilibrium. Rotational equilibrium. Now look at case number 2. When P vector is opposite to E vector, opposite to E vector, means theta equal to pi or 180 degree. In that case, sin theta is also 0, because sin pi or sin 180 is also 0. And again, if sin theta is 0, the torque will be 0. So under these two cases, whether the dipole moment is parallel or anti-parallel to electric field, we are getting 0 torque, tau equal to 0. And under this condition also, the dipole is under rotational equilibrium. So in the first case, the dipole moment is parallel to electric field, means here we have a minus q charge and here we have a plus q charge. So the dipole moment is directed from negative to the positive charge. So dipole moment and electric field have the same direction. In the second case, the dipole moment will be opposite to the electric field direction. Here minus q charge is on the right side, plus q charge is on the left side. So dipole moment will be towards left, but electric field is towards right. So they are opposite to each other. But under these two conditions, we saw that the torque acting on the dipole is 0. And when the torque is 0, the dipole is said to be under rotational equilibrium. But remember that theta equal to 0, this position theta equal to 0 means when the dipole moment is parallel to electric field, this position is known as the stable equilibrium position, is known as the stable equilibrium position. And theta equal to pi or theta equal to 180 degree, this position is known as the unstable equilibrium position, unstable equilibrium position. Theta equal to 0 is known as the stable equilibrium position, and theta equal to pi is known as unstable equilibrium position. Now the question is, why should we call this position as the stable equilibrium position and this position as unstable equilibrium position? We have to understand what is the meaning of stable equilibrium and unstable equilibrium. So students, remember that stable equilibrium means, suppose a body is under stable equilibrium. Now if you disturb its position, if that body again comes back to its initial position, then that position is said to be stable equilibrium position. Is that clear? For example, suppose you will take a bowl and inside the bowl you have a spherical ball or a spherical any sphere. Now at the bottom of the bowl, this sphere is under equilibrium. Now we have to test or we have to determine whether this equilibrium is stable or unstable. Now we have to do one thing, just disturb the position of the sphere. Now if I take the sphere to some height up to this point and then if I release it, what will happen? The sphere will again come back to the initial position. After a number of oscillations, finally it will come to the same position, and that's why this position is known as stable equilibrium position. What is unstable equilibrium position? Suppose a body is under equilibrium at a given position. If you slightly disturb its position, then it will never come back to that same position. For example, suppose we have an inverted bowl like this, and at the top you have a sphere, and the sphere is at rest, means it is under equilibrium. Now if I slightly disturb this sphere, then you will see that the sphere will fall down. It will not come back to this position again. Under these two positions, the body was under equilibrium, but the first one is the example of stable equilibrium. The second one is the example of unstable equilibrium, because here if you disturb its position, finally it will come back to the same position again. But in the second case, if you disturb its position, then it can never come back to the same position. So now on this basis we will understand why theta equal to 0 is known as the stable equilibrium position and theta equal to pi is known as the unstable equilibrium position. So let us draw the diagram here. Suppose we have an electric field, we have uniform electric field, and inside the uniform electric field a dipole is placed like this, and the dipole moment is parallel to the electric field. The dipole moment is from negative to positive charge, which is along the electric field. Is that clear? Now under this position, when the dipole is oriented like this, the net torque is 0, tau is equal to 0. Now if I slightly disturb the position, then what will happen? So initially this was the orientation of the dipole. Now I will slightly rotate it. So now the dipole will be like this, minus q and plus q. Is that clear? And this plus q charge will experience a force in this direction, minus q charge will experience a force in this direction, and these two forces will exert a torque. And this is p vector, this is e vector, the angle is theta. You can see that when you rotate the dipole in the anti-clockwise direction, you are trying to disturb the dipole orientation. Initially the dipole was parallel to, the dipole moment was parallel to electric field, and now I have rotated the dipole in the anti-clockwise direction. Now you will see that p vector is in this direction, e vector is in this direction, so the torque will be in the inward direction, means it will try to rotate the dipole in the clockwise direction. We have rotated the dipole in the anti-clockwise direction, but here when you disturb the dipole and then you release it, you will see that P cross E will be inward, means the dipole will be again rotated in the clockwise direction. So the dipole will again come back to the initial position, initial orientation. So this type of equilibrium is known as the stable equilibrium position. Now let us go to the second situation, when the dipole moment is opposite to electric field. The dipole moment is opposite to the electric field. We have minus q charge here and plus q charge here. The dipole moment p vector is opposite to electric field. Now if I slightly disturb the position of the dipole, suppose I will rotate it in the anti-clockwise direction like this, then minus q will be along this direction, plus q will be along this direction, and here p vector is along this direction and e vector is along this direction. This is p vector, this is e vector, p vector, this is e vector, and here you can see that the torque will be outward, because p cross e will be anti-clockwise, the torque will be outward. So when you are rotating it in the anti-clockwise direction, the torque which acts on the dipole, it further rotates it in the anti-clockwise direction. In the previous case, what is happening? We are rotating the dipole in the anti-clockwise direction, but the torque due to electric field was rotating the dipole in the clockwise direction. But in this case, we are rotating the dipole in the anticlockwise direction, and also the electric field exerts a torque which rotates the dipole further in the anticlockwise direction. Means the dipole will never come back to the initial orientation. Means if you slightly rotate the dipole, then the electric field will exert a torque which will rotate the dipole fully. Means minus q charge will come to left side, plus q charge will go to right side. The orientation will completely change. Means the dipole cannot come back to the initial position. That's why theta equal to pi is known as the unstable equilibrium position. Now the third case is case number 3. If p vector is perpendicular to e vector, if the dipole moment is perpendicular to electric field, in that case theta is equal to pi by 2 or 90 degree. And when theta is pi by 2, sin theta has the maximum value, that is 1. So what is the torque? The torque acting on the dipole will be Pe into 1 or Pe, and this is the maximum torque. This is the maximum torque acting on the dipole. So remember that the maximum torque acting on the dipole is equal to P into E, and a dipole experiences maximum torque when the dipole moment is perpendicular to electric field. So students, this is all about the torque acting on an electric dipole which is placed inside a uniform electric field. In the next class, we will solve some numericals related to all the concepts that we have covered till lecture number 10. So till then, bye bye and have a nice day.